Our ability to report the result of a measurement is limited by the accuracy of the equipment in which we have to measure and our ability to measure. So this is why we have to report uncertainties in a way that communicates our level of knowledge of the actual measurement we're taking. A measurement is recorded by stating the best estimate for that measurement plus the uncertainty contained in the measurement. We express that in this format. We say that the result of a measurement, in this case, let's say x, is equal to our best estimate plus or minus the uncertainty in that estimate. So again, this x best just represents our best estimate for the result of a measurement. That might be the height of a person. My height, for example, is about 5 feet 6 inches tall, but because no measuring device has unlimited accuracy and unlimited precision, and because our ability to measure is limited by that measuring device, there will always be a range of values and uncertainty in which our best estimate lies in. What is the uncertainty in the measurement of 110 centimeters? Or what about 11 centimeters? Or what about 1.1 centimeters? Each of these values were based off of the result of a measurement. And because of that, each of these values has uncertainty built into it. However, this doesn't follow the format of x equals our best estimate for the value plus or minus the uncertainty. Rather, here we're just given a single number. Well, how we could determine the uncertainty in these single numbers is based off of a convention that's used. This convention is called significant figures. And significant figures is a shorthand way of expressing a number whose uncertainty is given to be 1/2 of the smallest degree of measure. So let's look at 110 centimeters. This number is based off of an estimate. Now, when we talk about the rules of significant figures, we're going to see that this 0 is going to be considered insignificant, while this non-zero place is going to be considered significant. In looking at 110 centimeters, then, we are going to go to the place of the first significant digit. So the place of that first significant digit, which is the 1, is the tens place. The uncertainty in this measure is considered to be, by convention, when no uncertainty is explicitly listed, is 1 plus or minus 1/2 times the smallest division of measure. Here, the smallest division of measure, we are going to consider the tens place. So then the uncertainty in this measurement is plus or minus 1/2 times 10 centimeters, which is plus or minus 5 centimeters. This means that we could report the result of the measurement in the original way we have specified, and that would be 110 centimeters plus or minus 5 centimeters. This value and this value are equivalent. And the reason why we consider them equivalent is because whenever a single number is listed without listing explicitly its uncertainty, we follow a certain rule that says the uncertainty is given by plus or minus 1/2 times the smallest division of measure. Here, that smallest division of measure is going to be considered the tens place because the 0 in the ones place is considered insignificant. So if we go out to the tens place, we take plus or minus 1/2 of 10, which is plus or minus 5. That is our uncertainty. And another way of expressing this value is to say that that measurement is somewhere between 105 centimeters and 115 centimeters. Let's look at 11 centimeters. Let's say we have a measuring device. This measuring device measures in the centimeters, and I am going to mark out some centimeters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And let's say using our measuring device, we measure the length of a banana slug. And in measuring the length of the banana slug, we see that the banana slug seems pretty darn close to the 11 centimeter mark. However, the width of this ink I'm using in which to draw this image isn't 100% precise. Because it's not 100% precise, my measurement for the length of the banana slug has uncertainty in it. And by convention, we should be reporting the length of the banana slug with our best estimate. Our best estimate is the uncertainty our best estimate is based off of what we just measured, plus or minus the uncertainty in that measurement. So if you see this 11 centimeters and you don't see that uncertainty specifically listed, then it follows a convention. And again, the convention is the uncertainty is given to be plus or minus 1/2 the smallest division of measure. Here, the ones place is significant. And when I count significance, when we have a decimal on the right, and the decimal is implied to be to the right of that 1, then we count the first significant digit on the left. Here, that's the ones place. Since it's the ones place, the uncertainty in that length is given to be plus or minus 1/2 times 1. This value is plus or minus 0.5, and I should list our units. This is in centimeters. Uncertainties have units with them as well. This means that our report of 11 centimeters for the length of the banana slug is equivalent to look at this, 11.0 centimeters plus or minus 0.5 centimeters. Notice that the decimal of the uncertainty fixes the decimal of our best estimate, because since the uncertainty is to 0.5 centimeters, this is communicating that we were able to successfully measure the length of that banana slug to the nearest half a centimeter. However, because of our measuring device, we're only able to measure reasonably to the nearest smallest division of measure. And in this ruler, our smallest division of measure is 1 centimeter. And so we would measure our uncertainty to be plus or minus 1/2 that smallest division of measure, which is 1 centimeter. So plus or minus 1/2 of 1 centimeter is half a centimeter. And from this, we could reasonably estimate, whenever possible, if you could reasonably estimate to the nearest half of that smallest division of measure, then you can use the rules of significant figures. The rules of significant figures only apply to when you could successfully measure to 1/2 of the smallest degree of measure. If you can't make your measurement that precise, or if you can make your measurement more precise than that, then you don't use the rules of significant figures. You follow our convention of stating your best estimate, followed by the uncertainty in your estimate. But if you can state your result to the successfully and reliably to the nearest half of the smallest division of measure, then you can follow the rules of sig figs. Here, the significant figures will be 2 significant figures, and we'll talk about that shortly. Finally, let's do 1.1 centimeter. So let's say this is our measuring device. We will say this measuring device measures in 1, 2, 3, 4, 5, 6, 7, 8, 9. And so we will say our measuring device measures out to 1 centimeter. Notice the smallest division of measure is 0.1 centimeter in our measuring device. And actually, let's make our ruler a little bit longer. So this is 1.1, that's 1.2. Let's now measure the horizontal length of this line. When we measure the length of this line, there is going to be a certain amount of uncertainty in it. Is the line equal to 1.1 centimeter? Is the line equal to 1.2 centimeters? Is the line equal to about 1.15 centimeters? For the purposes of this discussion, I am just going to shorten this line a little bit. So based off of this line, we know that our line is somewhere between 1.1 centimeters and 1.2 centimeters, we think. However, I kind of just roughed drawing those dotted lines down. It could be that the line is a little bit less than 1.1 centimeters because I wasn't particularly precise in how I drew my dotted lines to measure the length. Here, I think you and I can estimate the length of this measurement to the nearest millimeter. Our smallest division of measure is the millimeter, and in fact, I bet we can estimate to the nearest half of a millimeter. This looks closer to 1.1 centimeters than it does to 1.05 centimeters. This looks closer to 1.1 centimeters than it does to 1.2 centimeters. It looks closer to 1.1 centimeters than it does to 1.15 centimeters. I think you and I can reliably measure to the nearest half of a tenth of a centimeter, or in other words, the nearest half of a millimeter. Since we are confident that we are able to do this, we could report the length of this squiggly line to be 1.1 centimeters, following the rules of significant figures. Well, again, the convention is if you could reliably report your measurement to the nearest 1/2 of the smallest division of measure, then you can follow the rules of significant figures. And remember, our smallest division of measurement is 0.1 centimeters. Since that is our smallest division of measure, and since we feel that we could reliably report to the nearest half of that, we could specify our uncertainty as plus or minus 1/2 of 0.1 centimeters. This is the same as plus or minus 0.05 centimeters. So our uncertainty goes to the hundredths place. Since our uncertainty goes to the hundredths place, that means that we could report our measurement to the nearest hundredths. So we could report this as 1.10 centimeters plus or minus 0.05 centimeters. And I see up here, I wrote a meters. That should have been a centimeters. So this value is equivalent to 1.1 centimeters. If we don't specifically state the uncertainty, we assume that we are taking plus or minus 1/2, that smallest division of measure. And remember, this means that our result, that our measurement, the true value, we believe, lies somewhere between 1.05 centimeters and 1.15 centimeters.